Greetings, the Astro 30 here yet again with a sort of experimentation video here. What we're looking at is a fairly simple 7 transistor discrete amplifier here, power amplifier, and it's not overly complicated, and you can always look at this type of schematic or this type of amplifier as in 3 stages. So here is the input stage, which is just a standard long tail pair. That's the voltage amplifier stage, comprising of a single transistor. In this case it's a BC546. And then you got your output stage. Now, I don't know where this schematic came from. I found it randomly on the internet when looking for something else. And apparently it's called the Digi 125 amp module, and it was made as a kit, but this is kind of reminiscent of old ETI or Electronics Today International schematics, which may or may not be where it came from. However, their claim is that if you use the original transistors here of the 2N305 and the 2N295 or MJ2955, you would roughly get 75 watt out of it. With the MJ802 and the MJ4502 you get 125 watt. And with the MJ15003 and the 15004 respectively, you'd get 200 watt out of it. And yeah, it also says over here for 200 watt version R6 should be 2K2 1 watt, which is there. Replace R7 and R8, these two here, with a wire link, so shorten them out, which would not be a good idea, because these are what are known as emitter degeneration resistors, and what they help to do is prevent thermal runaway in the output stage. So their claims of 200 watts is very optimistic. From a simple circuit like this operating on plus minus 37 volt DC, which is the maximum, so I ballpark it probably plus minus 35. Considering this topology, I doubt you get anywhere even close to 75 watt. Even that's optimistic. However, there are some good points about this amp and there are some bad points. The good points are it's simple, it will be easy to build on breadboard, bar the output stage transistors here, which I'll be mounting on a heatsink, and I'll be using TIP35 and TIP36C transistors respectively, instead of 2N3055s. There's not much in it. The bad points about this amplifier is there's no inline fuse protection, so there's nothing to protect the output stage from damage due to amplifier failure or even a short circuit on the output. That's the next point. There is no output short circuit protection, which would also comprise of inline fuses, but also what is known as a VI limiter, which limits the amount of voltage current, or basically the current flow going through the output during a short, limiting it down to, like, 4-6 amps max, and then having large enough inline fuses so that it doesn't false blow due to a short, but if the current got any higher it would blow the fuse. The other bad point is the choice of transistors for the VAS, which is the voltage amplification stage here. I was reading on the forum, which is the do-it-yourself audio forum where I got this from, that this transistor does tend to get quite hot under, well, even idle conditions, which is kind of a little bit concerning. And they were talking about putting a little TO92 heatsink on the transistor. Well, no. Personally, if it's doing that, I would change the transistor to something a little bit more robust, such as a BD139 transistor, and the drivers are BC546 and BC556, which in Darlington configuration, well, you can use a small signal transistor to drive a power transistor, that's no problem there, but I would still probably feel a little bit more better about myself, I guess, if these was BD139 and BD140. That's my take on it. They're using 3 diodes here in the biasing network, the self-biasing network, with the 2K2 resistor up here. And they use 3 to try and reduce crossover distortion and current dissipation in the output stage as much as possible. This is a Class AB amplifier. It's running in a gain of 22, which is average because of this 100k resistor feedback here and this 4k7 gain resistor here. You do the math, it's 1 plus resistor feedback divided by resistive gain. That gives us 22 approximately. It's 22.3 something. The other bad point is there's no RF suppression on the input. So what we would normally see here is, say, a 1K, maybe even a 2K2 resistor here between the base and this ground reference resistor, as well as a capacitor of around 330 to 470 microfarad, picofarad rather, from the base to the ground, just to prevent it from amplifying radio frequency interference. There is also no input bypass capacitor, which is also not a good design there, but that's easy to add. There is also no Zobel network on the output, which would comprise of a 10 ohm resistor and, say, a 100 nanofarad capacitor going to ground wide in series between the output and ground, to prevent this from going into oscillation, high frequency oscillation. And I will probably add that because, yeah, there's nothing worse than having an amplifier oscillating at high frequency, and of course you won't hear it through the speakers, but the output stage heating up red hot because there is no consideration of protecting the output stage from oscillation and making it more stable. Another thing I'm not happy about is the way they've got this 100 nanofarad bypass capacitor for the supply lines. They've got it going between the positive and the negative. This is fine if you're using a green cat capacitor, because they were normally rated at around about 100 volt anyway. Because we've got a plus minus voltage here of 37 volt, so added together that's 74 across that capacitor. And if you're using, say, something like one of these style capacitors, they're only rated for about 63 volt, because it actually says there 63, which means that's the maximum voltage you can put across that capacitor, albeit this is a 0.22 or a 220 nanofarad, but you get the point. If that was across the plus minus 37 voltage rails there, it would not last very long. So that's something to keep in mind with that we shouldn't do that. We should have one here and one there, both going to ground. It's only an extra capacitor. I mean, who cares, right? Points of interest could be that this could be bootstrapped by adding a voltage divider here of 2K2 resistors, putting a 100 microfarad, get it out, capacitor across here to the output, to bootstrap this to give the output stage a constant current source. But that's something to experiment with. The other thing that may be an issue is the 150 picofarad millicapacitor choice here may be a bit too high. That remains to be seen. If it starts going into some ultrasonic oscillation, that would be something I'd look at, is this millicap. Reading the same forum, it was saying that this 47k resistor in the long tail pairs emitters here should be 4k7, not 47k. It's too high. And looking at it, yeah, compared to what's down here, it does look too high. So the next step would be, rather than talking about it, oh, and the other thing is, ETI often did this with output stages. They would put two 1 watt resistors in parallel to get 2 watt ones, rather than using 5 watt ceramic or 5 watt cement type resistors, because this is reminiscent of the old ETI 480 power amplifier module, Just saying, for those of you who know that module. And when you went for the 100 watt version, which had 2 output transistors, they would have under the board, joining to the collector, I think it was, in that one, 2 of these wired back to back, so it would stick out the edge of the board with these 2 resistors wired in parallel going to the transistor. I just made the tripod. Going to the transistor, and it looked fucking ugly. Anyhow, that's beside the point. So let's get this breadboarded up. I'm going to add an input cap, obviously, to start with. Then we'll worry about RF suppression. Don't know whether to try it at the 47K or just go straight to 4K7. Don't know. And then change these to 0.47 ohm resistors here, just 2.5 watters. I'm going to use the same stage that I had built in the last video, except I'm obviously going to reverse the wiring on the transistors. By the way, this is an emitter follower amplifier with a Darlington output stage. Anyway, sorry for the long intro, but I just needed to make some valid points about this schematic of what its bad points are and what its seemingly good points are. But I doubt this is going to get anywhere near even 75 watt. I'm going to go out on a limb here and say off the bat, because I'm going to do my testing on plus minus 25 volt to start with, we're going to see no more than about 20 to 25 watt out of this thing. But it remains to be tested. Okay, so I've got the input stage built now, and what I thought would be probably a good idea to do here is to just run a test on the differential pair here. In order for me to do the other channel, I'd have to add another 22K resistor to ground on the input of this transistor on the base here, because this is the inverting stage and this is the non-inverting stage transistor over here. So hook up an oscilloscope to the output of the transistors here, which is formed at this point here, at this collector here via this resistor, and just see by pumping a voltage in here what happens at the output compared to pumping a voltage in at the base of this one. So let's get that done. I'll just add a 22K resistor between this base and ground, so that's actually doing something. Okay, got everything hooked up here. The DDS at 1 volt peak to peak, 1 kilohertz, power supply roughly around about plus minus 15 volt for this test. Oscilloscope connected to the collector output. So let's turn the power supply on. And we do indeed have an output, albeit it doesn't look all that pleasant, but we do have an output. So if I switch the input to the other side, we can see we have an output also. It looks a little bit different. It actually looks like it's clipping more than anything else. That looks like it is clipping, but weirdly. So let's drop our input sensitivity down to say 200 millivolt. Now that looks a bit better. It's a nice sinusoidal waveform there. So currently we're getting 12.1 volt peak to peak out. Okay, so we're getting, what did I say, 12 point, we'll ballpark it at 12 volt peak to peak, and then we divide that by our input voltage, which is 0.2 for 200 millivolt. We've actually got a amplification of 60 times there. That's not too bad. So we know that the input stage is working, so I'll just move the input over to the other channel. Now the only thing is, this oscilloscope doesn't show whether or not it's inverted or non-inverted. It just looks exactly the same, but trust me, this side would be 180 degrees out of phase with that side. It's just that on this small little JYE Tech oscilloscope, it can't be seen. So if I increase my voltage up to 22 volt, we can see the output voltage swing is also increasing. Same as if I decrease the voltage, my measured voltage also decreases to the point where it doesn't work anymore. So even at 18 volt we're getting 13 out. We're getting a loss, but that's just the nature of this type of circuit. Just going to make sure that these transistors are not getting hot, which they're not. And look what happens when I touch the inverting side capacitor's lead. See what it does to the signal? So that's basically what negative feedback will be doing to the circuit. Remember, putting negative feedback into the inverting input of the amplifier is going to affect what's coming in at the non-inverting input, because the two transistors work together. But we know that that stage is working, so the choice of 4K7 there instead of 47 in the emitter resistor, or emitters resistor, I'll get it right in a minute, was a good choice. Okay, well, I've gone and built the rest of the circuit up. Wasn't that hard. I made a couple of mistakes in wiring and rechecked it all now, and it is wired correctly as it should be. I haven't connected up the positive and negative supplies for the output transistors yet, but I'll do that in just a sec. I've still got the DDS set to 1 kHz 200 millivolt peak to peak. I've got the output junction here connected to a dummy load across the oscilloscope, times 1 probe, and I'm going to start at 15 plus minus volts on the power supply, current limited down to less than an amp, just in case things go south. So I'll connect up the supply wires for the transistors, and we'll see if anything goes off with a bang. Okay, with that done now, I'm going to turn the power supply on, and hopefully nothing goes off with a bang. Well, we've actually got an output too, but I was just looking at the current. Current draw's not too bad. At 200 millivolt peak to peak in, we actually do have a nice 4.86 volt coming out, drawing no more than about 300 mA on the current at the moment, and the output stage is still cold. So as an amplifier, it is indeed working. Just touching the top of the VAS transistor, it seems okay at the moment, but 200 millivolts is not a lot. So what I'll do is I'll increase the amplitude to 1 volt peak to peak, my standard. And we're going to hit current limit on the supply because I have it turned down. So I'll back the current limiting off. And now we're drawing closer to an amp. But we still do have a relatively clean sine wave. And I'm still only at plus minus 15 volt here. So going up to, say, 20 volt plus minus on the power supply. Current draw is around about close to an amp. I mean, that type of meter on there is a pain in the ass because it's not stable. But it reached about 900. So I'm just going to change my time base here so we can see the sine wave just a little bit better. And that's not entirely bad. That is quite a good sine wave. And we're getting a good 22.5 volt out, which is not bad. And the output transistors aren't even getting mildly warm. As for this issue with the VAS, yeah, it is getting quite warm. So it might be in its best interest to change that. Drivers, not even hot. Okay, so next thing I need to do is to figure out, at plus minus 20 volt at least, what its maximum output is before clipping. So I'm going to increase my amplitude to, I don't know, I'm just going to go 1.3 volt. Still okay. Go to 1.5. Still okay. Let's go 2 volt. Now we're clipping. So if I back that off till clipping goes away, which is about there, I am getting 30.82 volt peak to peak out and drawing around about 1.5 amps. And the output stage is still not getting hot. The bass, not too hot to be concerned with at the moment. So at 30.8, divide that by 2 equals 15, times that by itself, 237, divided by our resistive load. Well, it's 29 watt peak. The actual average power using the RMS voltage value. Okay, so our RMS voltage is 11.5, so it's going to be less than 29 watts. 11.5 multiplied by itself equals that divided by the load. Quite an impressive 16.5 watts. Not bad. So that little amplifier circuit is quite good. I mean, I've had very little success with building amplifier schematics, random ones like this, off the internet and having them work straight out the box. But yeah, that plus minus 20 volt power supply with a 1.5 peak to peak voltage input, we're getting a nice clean 31 odd volt out. So that's not bad. So let's go up to the 25 volt plus minus voltage that I wanted to be at in the first place, which is around about there. Now, as for our voltage input before clipping is concerned, that should now have a little bit more headroom. We're now at 2 volt peak to peak, and it's clipping. So I'm going to say 1.8 volt peak to peak is nice and clean, and we're now getting more like 37.7 volt out. So 37.7 divided by 2 is 18, multiply that by itself equals that divided by the resistive load, 44 watts peak, and our RMS value is 14.1 roughly. So 14, we'll say 14, multiplied by itself, divided by the load. Well, my prediction of 25 watts was around about right. There we go. So if this circuit was running at the plus minus 35 volt rail, we'd have a little bit more headroom on our input peak to peak voltage. I mean, for all intents and purposes, I could wind this all the way up to 30 volts. Which it's not going to get to because of the amount of currents being drawn. And that should mean that I can now increase this so I'm more like 2.1 volt, and I'm getting 42.5 out and 16.6 RMS. So for safety reasons for now, I'm just going to back that off, and I'm going to put this amplitude back to 1 volt. However, it does look like we are suffering from a little bit of crossover distortion here, because it's not a perfect sine. If I drop the voltage down to 500 millivolt, just for the sake of doing it, yeah, that's not particularly sinusoidal, is it? So I'll just turn the load off and then back on again. Yeah, it's not a stabilisation issue. So we have got quite a bit of crossover distortion there. So what I need to do is I need to, in this biasing resistor, yeah, that VAS is getting red hot, that needs to be changed. In this biasing resistor here, I need to put a potentiometer to see if I can adjust out that crossover distortion. So that's the next thing I'm going to do when I can find out what I did with my pot. So I've got a 50k pot wired across the positive and that resistor in series with it. As a bias adjustment, if I now play with this pot, that was easy. So 2K2 is too low for a start. So that's with a voltage of 26.2 volt peak plus minus going in. So I'll take the amplitude back up to 1 volt peak to peak. See how that looks nice and flat now? And actually we can even ballpark it even a little bit further. So with the time base right down, I'm going to play with this and we can actually see that's exactly what crossover distortion looks like. See that little hump there? And of course it's more pronounced at that point, but see it's almost gone there, pretty much gone there. So the rest of the rotation of the pot's not making much difference, A, to the output or to the crossover distortion, but it's pretty much gone there. So what that means is I now need to measure what the resistance of that potentiometer is and then add the 2K2 resistor to it. But as I said, I was going to bootstrap it. So what I might do is, well, we can then work out what our potential divider needs to be via the resistance of this, and that makes bootstrapping it a lot easier. So let me just go and measure the resistance of that. Right, well that measured at 15k, so I've stuck a 10k in there for now because there wasn't much difference between the end of the rotation and where it is. And we do indeed still have a nice sinusoidal waveform. So I'm not particularly worried about using a 10k there instead. The VAS getting hot is a concern, so that'll be the next consideration. But first what I'm going to do is I'm going to bootstrap the output, just to give the output stage here a constant current source. I'm going to use a 100 microfarad capacitor, positive going between the 10k and 2k2, and the negative going to the output side. So let me do that. Okay, so the output is bootstrapped. Turn the load on. So now we can actually see what the difference is between bootstrapping and non-bootstrapping. Now notice that we're getting a waveform that keeps moving around between 21.2 and 21.7 thereabouts. So I'll turn the load off and I'll reconnect the capacitor. That's without bootstrapping. This is with bootstrapping. Notice how it's now more stable around 21 odd volt. Looking at, is that an 8 or a 0? No, it's 21.8, so it's actually increased it a little bit, or at least kept it stable at 21.8. Yeah, 21.89 volt, or 7.5 odd there for RMS. So the next thing to do would be to address the VAS getting red hot. I'm going to insert this BD139 NPN transistor in its place of the BC546, and well, if this gets hot, that means it needs a heat sink. But, well, it's not getting much that hot now, but it is still getting hot enough to be concerning. Okay, and there's the BD139 in there. All I had to do was reverse a couple of these wires around and that diode, because the pinout is slightly different. It goes emitter, collector, base when viewed from the back. But now to check that it still works or goes bang, so I'll turn the current limiting back down to about 500 mA and then turn the load on. We have an output, but it's albeit bad. So let's take the current limiting off, and there we go. Just was making sure. Now that's what happens when you current limit it. It did reach current limit, and that's the result. That's fine. It's still working as an amplifier. It's still not drawing any more than about a little over an amp at 1 volt peak to peak in, and we're still getting 12.89 out. So that should address the bass. Just doing a heat test on that, because that should have a larger die than the BC546, so it shouldn't get anywhere near as hot. It'll get warm, yes, but at the moment I can't feel it. I'll keep checking it periodically. Okay, that's the circuit built and working nicely. It's time to do a customary sweep test and see what the frequency response is.
He's an idiot.
Of course, being serious about it at the same time. It's not overly bad. Getting a little bit of roll off around about the 18 kilohertz range. It's remaining relatively stable. And relatively flat, I mean. So, okay. Guess what? That bass is not even warm. Those output transistors are, though. But, yeah, it is sinking the heat. So, I'll turn the power off, and I'm going to get set to do some audio output test, or output tests. I don't even know what I'm talking about now. Okay, before the sound test I just did some modifications off camera, and I've got a Zobel network here consisting of this resistor and that capacitor. When I connected it across the negative point of that capacitor, which is the feedback network from the output, it started giving me weird results, like crossover distortion badly. When I connected it via a wire, jumper wire, directly to the output point, well, problem was solved. I've also got a 330 picofarad between base and ground here at the first transistor, a 1K at its base between it and the input capacitor. But everything else is the same. Got it hooked up to a speaker, so I'll put it in current limit mode just in case something goes strangely wrong due to modification. Apparently not. Except now I have no output, which is odd. I should have an output. Take two, it helps if the jumper wire was actually connected to the wire and not the insulation. Oh. Yeah, it works. There's a bit of a thump there. Okay. Now, I need to hook it up to a source of audio, I suppose.
Perfect.
Sounds okay for what it is. However, the amount of idle current draw there is 140 mA, which is kind of a little bit concerning. It shouldn't be really any higher, in my opinion, than 50 mA. Okay, so before I end this video, let's have a look at the completed, finalised schematic here. I've chosen to put 2 amp fuses in line with each of the supply rails, which may be a little bit conservative. I need to plug the thing in. Take 2. I've got two 2 amp fuses in line with the both supply rails here, which may be a little bit conservative. Probably more like 3 would be more the ticket there. I am going to plan on adding a PTC on the output there as short circuit protection. As we can see, we've got a 10 ohm and 100 nanofarad capacitor there as the Zobel network. Most of it's the same apart from the VAS is now a BD139. We have this voltage divider here in the biasing network with a bootstrap capacitor. Now, this is what would be causing most of the pop at turn on, because this capacitor is discharged and therefore this resistor and this capacitor are now acting like an RC delay. So we have to wait for that time constant to expire for it to charge up to the voltage that it needs to be, which is the supply voltage with reference to ground, which will be reference to output here, divided by the drop across these two resistors. If they were even and the supply voltage was 20 volt plus there, it'd be 10 volt here on the capacitor. But it'd be more like, probably in this case, 15, something like that. The input stage has changed. We've added an input capacitor, a 1 kilo ohm stopping resistor for RF blocking, plus this 330 picofarad capacitor to ground across the base, just for added RF filtering. Other than that, the circuit is the same as the one that I downloaded, albeit this 100 nanofarad is now referenced to ground, not the negative rail. We've got another one here on the negative rail reference to ground, and we've also got two 220 microfarad capacitors here as bulk filtering after the fuses. The only thing that is kind of concerning is the quiescent current that the amplifier is drawing when idle, which is 140 mA. And I noticed the PNP transistor, the TIP36, was getting warmer, plus its degeneration resistor, than its counterpart over here. So that's really hard to pinpoint. Because it's on breadboard, breadboard does not make an audio amplifier layout. Layout of power amplifiers especially is vitally critical. You've got to have all your grounds returning to a central point. All the outputs have to be pointing to a central point. They can't just be wires all over the place like I have on the breadboard, because that adds extra capacitance and also can add RF interference, and it does all sorts of funky things to the circuit and can skew your test results. But for the interim, it works. It tested okay on breadboard, looks fine on an oscilloscope, sounds reasonable through a speaker, albeit a little bit distorted. That's probably the laptop again. But yeah, what the next step for this would be to make up a PCB for it. Why not? I can. And then I might release the Gerber file for that, for anyone that wants to make the circuit board professionally or whatever, as well as the copper artwork at 300 dpi, the silk screen at 300 dpi, and all that nice stuff. Before this video goes live, I will draw up this schematic properly in a CAD program. I'll link it in the description, and I'll also link in the description where I found the original schematic. It comes off the Do-It-Yourself audio forum. Yeah, you can take a look at it. This is open to further modification. I mean, to get that quiescent current down in the output stage, we could add a VBE multiplier instead of these string of diodes here, or as what's also known as a bias spreader. But for the simplicity of the circuit, I didn't see the point. Plus that means the VBE multiplier also now has to be in contact with one of these drivers to adjust the bias accordingly. And the same is also true for these diode strings. They have to be as close to these two transistors, these driver transistors, as possible when it's on the board layout, so that the heat can thermally transfer into the diode, making the diode conduct more, therefore reducing the current through the output stage. That's how it's supposed to work, and that should prevent thermal runaway. Having them in close proximity to these type of signal transistors will work to a point. It really does have to be in thermal contact to work efficiently, but even if it's just close enough for the heat coming off this transistor to affect the amount of conduction this diode is doing, the same down here, will help matters a lot. Having three here, for crossover distortion, it didn't really seem to help, not in its original configuration, but it could also be the choice of output transistors could be mismatched for the circuit as well. Matching complementary pairs is always mandatory, really, when building the output stage. But the way this bias network is set up now, it should allow for different various output transistors. I just chose TIP35C and 36C because I had them. You could easily just use 2N3055 and MJ2955 respectively, or TIP2955 and TIP3055, 2955 down here. Anyway, that's going to do it for this video. Thank you for watching, and if you enjoyed it, please remember to rate, comment and subscribe below. And you can always follow me on Facebook. The links are in the description as usual. Anyway, can you please press the start button and then hold it down at the control key? Anyway, this is the Astro 3 saying see ya. Have a great day.